in lesson 3.2a, we're going to hone in on a specific type of function, which are linear functions. So we're taking lesson 3.2 and we're splitting it up over 2 days. And on this first day, our main primary focus will be just being able to identify whether or not a function happens to be a linear function. So in the previous lesson, we identified functions in general, and now we're going to just be a little more specific and find out, does it belong in this particular family of functions that are linear functions? Still review, you guys have talked about linears before, constant rate of change, something that is increasing or decreasing at a steady constant rate of change every time. We're going to just review what that might look like in equations, on a table, and on a graph. What we have an example here of a mapping diagram too, but the most common representations for linear functions is going to be being able to tell if something is a linear function when it's represented in an equation, when it's represented on a table of values, and when it's a graph. So again, quick review. We're looking for constant rates of change, a constant either increase or decrease in your output for every change in the input. So if things like the change in y over the change in x sound familiar, eventually we'll be talking about slope, y-intercept. If all that kind of rings a bell, then that's good news because you know where we're headed with this, okay? So quick review, just let's talk about equations. So in an equation, one of the main giveaways that you have a linear function in that equation is if when you're solved for y, you have an x term that is just a pretty basic x term. It can have a coefficient. It might have 2x, 5x, negative 4x, but it has no exponent, and x is never in the denominator. So the primary qualities that we're looking for is that it's just an x term, okay? If it's an xk or xy, where it's got multiple variables, that is not going to be a linear function. If x is in the denominator somehow, down at the bottom, that is not going to be a linear function. If there is a power or an exponent on that x base, that is not a linear function. So we're looking for just a regular x term. It can have numbers in front. This one does not, but you'll see, well, it does. It has a 1, right, even though we can't see it. But, you know, we'll see other examples that do have a coefficient attached to it. That is okay. That is just telling us how many x's we have. But they still should be just x terms, okay, in an equation. And if that is the case, and there is not any of those other qualities like exponents or other variables attached or x in the denominator, then we can confidently say, yeah, you know, that's going to be part of the linear function family. Okay. In a table, we're looking for the constant rate of change. So we're looking at comparing how are the values increasing or decreasing compared to the x values, how they are increasing or decreasing. So if I look at my y values here, from 2 to 3, I increased by 1. From 3 to 4, I increased by 1. And from 4 to 5, we increased by 1. And then I'm going to compare that to the changes along the x-axis. So from negative 1 to 0, I increased 1. From 0 to 1, I increased 1. From 1 to 2, I increased 1. And these don't have to match, but what does have to match is that the change in y over the change in x, that ratio is the same every time. So if I compare how much did y change over how much did x change, this is a delta, that's the symbol for change. For this one, the y changed 1 as the x changed 1. So that has a 1 over 1 comparison there, right? The second one here has 1 over 1. That is the ratio there of the change in y over the change in x. For this last one, the change was 1 over a change of 1. And because all of these change in y over change in x ratios are the same, that's how we know that that is a linear function. Okay, mapping diagram would show something similar, where we would have only one arrow pointing to only one output, right? So we said last time that multiple arrows coming out, just that's not even a function, right? But even in the function family, sometimes like I have -1 pointed to 2 and then 0 also points to 2, and that's okay for a function, but not for a linear. A linear would be, one arrow to one output every time, just like you see here. And last but not least, on a graph, is probably the easiest one to tell. You know you're looking at a linear function if the entire graph is just a straight line that never changes direction. Just a straight line, okay? If it's got different parts that are straight, but it changes direction, kind of like some of these function examples that we had last time, that's not linear. Because even though they're straight, they change direction at some point, right? Same thing here. Okay, but if the entire graph is just a straight line, a straight path, and it never changes direction, then you know that that's what makes that linear. Okay, so let's just practice identifying whether the following functions are linear or nonlinear. Okay, for now, that's just as simple as we're going to keep it. If it's either linear or it isn't. Okay, and we're just going to focus on that. Okay, so starting with a graph, probably the easiest one. We'll start with the easiest here. If you look at a graph, like I just mentioned, you're looking for a very straight line, straight path that does not change direction. And if it makes it easier on you, use a straight edge to kind of compare. Pretty quickly, you're going to notice that this is not a straight line, right? If we put a ruler or a straight edge up against that, it definitely has some curve to it. That is a deal breaker. For a linear, it would have to be a perfectly straight line that never changes direction. So the fact that this curves this way, it might be a function. It actually is, right? This passes the vertical line test, but it is not a linear function. So this is what we would call a non-linear function. Because a graph is not a straight line. Okay. Number 2 does definitely appear to be a straight line. If I take a straight edge up to it, it definitely fits that pattern of just a nice, straight, smooth line. It keeps going on, and it never changes direction. This is a linear function. Okay, so from a graph, it's pretty easy. As long as you know what you're looking for, all you have to do is look at it and be able to tell. You don't have to do a whole lot of work. The table definitely requires a little bit more computation. Okay, we're looking here for that rate of change compared in y compared to the rate of change in x to be the same every time. So we're going to do a little bit of comparison here. First, let's find out how did our x values change. So from 1 to 2, that was an increase of 1. From 2 to 3, that's an increase of 1. From 3 to 4, that's an increase of 1. Okay, let's compare that to our y values. From -1 to 2, that went up 3. That increased 3. Okay, so this x over y, change in y over change in x ratio, if we compare how did the y change over how did the x change, the y changed 3 points or 3 values. It increased by 3 as x increased by 1. So that would be this first change in y over change in x comparison. Then for the next one, if I go from 2 to +5, I also increase 3. So that ratio is also 3 to 1. Okay, so that's a 3 over 1 ratio or comparison of how y changed over how x changed. And then 5 to 8 also increased 3. So again, I compare that change in y over change in x ratio, and it was the same for all of those, right? So in every one of these, as x increased by 1, this increased by 3. It's a constant rate of change. That is what makes it a linear. If you plotted those points, they would graph in a straight line path. So this is a linear function. Okay, let's take a look at this table and do the same analysis on it. Let's look at to see how x changed from -1 to 0. It increased 1. From 0 to 1, it increased 1, and from 1 to 2, it increased 1. They're keeping it fairly comfortable for us by keeping that x going up by 1 every time, so we can see the pattern in the y's. They won't always be that nice, but right now, as we are introducing this, that's actually helpful, because then we can really say, okay, if this constantly went up by 1, then we can really focus on, is this always increasing or decreasing by the same amount? So let's try it here. From 0 to -1, that actually decreased by 1 unit. Okay, it went down by 1. And then from -1 to 0, it actually increased again. So it went down and then it went up. That right there is our deal breaker. Okay, so when I compare that -1/1 to +1/1, I don't get the same ratio. And then in the next one, it really seals the deal here, because from 0 to 3, that's an increase of 3 units. Okay, so even though this was just going up 1, by 1, by 1, by 1, just going up 1 every time, this was not maintaining a constant change. It decreased by 1, then it increased by 1, then it increased by 3. Okay, so there's not a constant rate of change. If we plotted these points, they would not be along a straight line path. Okay, therefore, this is a nonlinear function. Okay, so those are the patterns that we're looking for from the table. That's probably the one that requires the most work. On the graph, you're just really looking at the picture and looking for that straight line that just doesn't ever change its direction. The equation, you're also just going to be on the lookout for specific qualities. This is the one that really makes you do some work to make sure that those points are on a linear function. Okay, so let's talk about the equation. Remember what I said. In order for it to be linear, it needs to just have a y term and an x term. No exponents, no x's in the denominator, no x's connected to other variables, nothing like that. It's just a regular x term. It can have a number in front, like this has a -2, but that's just telling me I have -2 x's. This is still an x term, okay? So y equals 3 minus 2x is linear because there's a y term and then there's an x term. It's okay if there's a constant. In fact, if you recall, y equals mx plus b, there usually will be some y-intercept and then the x term with the slope. That's all just foreshadowing what we're going to. But the main thing is that when you're looking at your variables, there's a y term, a regular just plain y term, and a regular plain x term. This will tell me how many x's, but they're still just x's. So this guy right here represents a linear function. Okay. Now, if you compare that to number 6, right away, when we look at that, okay, the y is by itself, it's a regular y term, no big deal, equals, and then this is fine, but right here, this is where my deal breaker is, okay? This is not just an x term, it's an x to the 3rd power term. It is an x cubed. And that exponent changes what kind of function this is, okay? It is not, if you were to put this in your calculator right now or on Desmos and graph it, you would get a graph that is definitely not a straight line, because that exponent does very different things to your points and to your graph that make it not be a straight line. So this is a nonlinear. So non-linear function. Okay, let's practice a few more so that you feel comfortable identifying whether a function is or is not linear. Let's take a look at 7 and 8 here. Same thing, graphs, probably the easiest one. We're looking for a nice straight line that never changes direction. It should have no curves, no corners that change directions. And this is an excellent example of a linear function. It's just a nice straight path. It has the same direction everywhere, and it has arrows saying it's going to continue in that same direction. So this is definitely a linear function. Versus this guy right here, okay, which still passes a vertical line test. It's a function, but definitely not a straight line, right? Very quickly, I can put a straight edge to this and realize, oh yeah, that's not a straight line at all. Okay, it's got all kinds of fun curves here, and then a little plateau, and then comes back up. This is a nonlinear function. Okay. From a table, that's usually where we have to pay a little bit more attention. Okay. We're going to compare how the x's are changing. Okay, so here 0, 1, 2, 3, all those x values are just increasing by 1. They kept it nice and simple for us there. And let's see what are the y's doing. From 3 to 5, it increased 2. From 5 to 7, it increased 2. From 7 to 9, it increased 2. And so when I compare that change in y over the change in x, we always put the y on top, right? This right here has a ratio of 2 over 1 when we're comparing that change of y over the change in x. This is a 2 to 1 ratio, and that is a 2 to 1 ratio. They all have the same 2 to 1, 2 to 1, 2 to 1, constant rate of change. Okay, constant increase or decrease. This is linear. It is a linear function. Okay, let's check number 10. And this is a modeling the level of work that I would expect to see in order for you to get credit, and I would know that you have good evidence for making the decision that it is or it isn't a linear function. So on this one, our y values went from 1 to 4, from 4 to 7, from 7 to 10. This is increasing by 3 every time. It went up 3 every time. So it's not always a 1, but it still went up by the same amount. Okay, that's still pretty helpful. When I look at my y values, from 2 to 5, it increased by 3. From 5 to 6, it only increased by 1. And from 6 to 10, it increased 4. So when I do the same thing here and compare the change in y over the change in x, this ratio was 3 over 3, which is the same as 1. This ratio is 1 over 3. That is not equal to the first one. And this one is 4 over 3, which is also not equal to either of those, right? So our change in y over the change in x is not the same. It's not a constant rate of change, okay? That makes that a nonlinear. Nonlinear function. Okay. Let's practice from equations and then we'll be good to go. Okay, so we got 11 is y equals the square root of x plus 5. I have a regular y term, that's fine, but my x is not just a regular x term. It's trapped inside that square root. It's a square. I don't have x, I have the square root of x. Having that square root symbol around my variable is a deal breaker. If you test it and graph that, it would not graph as a straight line because this is not just a typical x term. It's the square root of x. It's a different type of function. Okay, so this is non-linear. Okay, and again, it's because of this right there. Okay. Number 12, I have a regular y term equals, and then I have 4x minus 2. This is my x. This is a regular x term. 4x just tells me I have 4 of those x's, but they're still just x's. And so this is linear. Okay. Number 13, think about that one. That one is going to be linear, right? Because you have just a regular x term. Y term on this side equals 9 minus x. This is the same thing as having like a negative 1. It's just telling me how many of those I have, but it's still just regular x's. So that's totally fine. Okay, and then that would make this linear. Okay. And last but not least, number 14 on this. This one's a little trickier because I certainly see x and then a regular x, but they are matched up together, like, you know, they're up against each other through multiplication, which basically means that all of this stuff is going to get multiplied by all of that stuff. So this whole group is being multiplied by that whole group. And that means that at some point you're going to take x and multiply it by x. Well, when we multiply x times x, we end up with x to the second power. So as you do this mathematics, you would have found that an x times an x, which is what was happening here since all of this is getting multiplied by all of that, that an x times an x is going to give us an x to the second power, and that is a deal breaker. Okay? It's not going to graph or act like a linear function. So this is a nonlinear. Remember that exponent is a deal breaker. Okay? So that's identifying. Hopefully you feel comfortable looking at a graph, looking at a table, looking at equations, and being able to say, yes, it is linear, no, it isn't. And an equation, and one easy way to tell is if you solve it for y, you should always be able to write it in that y equals mx plus b. I know we haven't formally gotten to this, but I know you've done this in the past. So I know that you can identify it if you get y alone and you end up with just an x term and just a constant, and you can make it look like that y equals mx plus b, you know you're in good shape to say, yeah, that's a linear equation or a linear function. Okay, the last one is kind of working backwards from the table. You are being told it's a linear function, and we need to figure out what these values might be. Okay, so fill in the table so that it represents a linear function. Okay, this can be kind of tricky. In fact, we probably will use a little bit of slope stuff here to help us out. It looks to me like we're going from 4 to 20, and we're going up by 4 every time. So when you look at this pattern, we're just going to explore this pattern here. They're adding 4, they're adding 4, they're adding 4, and so forth, right? So it's really an increase of 16 units, and they added 4 every time. Well, somehow in the same increment of numbers, we have to get from -4 to 12, okay? That is also an increase of 16. Okay, and so I went from 4 to 20, that's increasing by 16, and to get from here to there, we had to add 4 every time. Here, from -4 to 12, I need to increase 16 as well, and I have just as many slots to do it. So I'm thinking adding 4 every time might work, so let's try it. If I add 4 here, I would get 0. If I add 4 again, I would get 4. If I add 4 again, I would get 8. And if I add 4 again, boom, there I would be at 12, okay? So I was able to find this sort of total distance I wanted to go across, and then figure out what I needed to go up so that I could fill those in. So increase by 4, increase by 4, increase by 4 does the trick so that it is linear. It has that constant rate of change all the way down, and I'm able to, get exactly the number of values I need for the table. All right, that one's kind of for fun, a little more challenging, a little higher above. The most important part is being able to look at an equation, look at a table, and look at a graph, and be able to identify, yes, that's going to be a linear function, or no, it's not.